Our second speaker will be Shai Evra, who is a first-year faculty fellow at the Einstein Institute of Mathematics at the Hebrew University. And today he'll be asking, can number theory protect our messages? Shai, please feel free to begin.
Okay, so let me just share my screen. All right, so first of all, let me thank the Azrieli organizer for this wonderful event and the opportunity to present my work. So my name is Shai Evra. I'm a mathematician, and I would like to tell you about how number theory actually is being used in our day-to-day lives. So I would like to begin with the following question. We are all living in a quite digital lifestyle, having our phones and our computers and sending text and messages and emails. And I wonder if you ever ask yourself, how is it that when you send a text or an email to someone, a friend or a colleague that could be halfway around the world, he gets the exact text message or email that you sent him. No errors occurred. Every word that you wrote, he gets the precise word. I think we're all familiar with the broken phone game where I tell a friend of mine some message and then he repeats it to his friend, but he slightly changed what I originally said. And then that friend repeats it to his friend and the message gets slightly more distorted and so on and so forth. How come that doesn't happen with our messages, our digital messages? So the answer comes from a theory within theoretical computer science, which goes under the name of an error correcting code. So this is what we have in all of our phones, in all of our computers. And let me show you how the scheme of how an error correcting code works. So it is very custom in computer science. We have two individuals, Alice and Bob. And suppose Alice wants to send a message to Bob. Now, if she would just send the message as is through, say, through some copper wires or some fibers or through the air, the message would get distorted because there's noise everywhere. So what an error correcting code does is it takes the original message that Alice wanted to send, and then it encodes it. It added some extra bits, an extra layer of protections to the original message, making a coded message. That coded message goes to the noisy channel, and error might occur. So what you get at the end of the noisy channel, you get a slightly corrupted message. But if the code is good enough, then you are able to extract the original message from the slightly corrupted coded message and get the original message of Alice, and that is what Bob can read, and this is what we are all reading. Actually, we are all getting it at this moment. As I give this talk, an error correcting code makes sure that what I'm saying is being translated, hopefully it's being translated to all of your computers. Okay, so what do I do? I'm not an engineer. I don't physically build the codes into the computer. I'm a theoretical mathematician. And so I like to think of a code in a more abstract way. And there is a way to present a code by an abstract graph, just a collection of vertices and edges. And the way that you do it, you basically, for this example, I'm going to just show you an example of one code, a very famous code, in which you, the coded messages that you keep send are of length 5, which is the length of the number of vertices on the left side of the graph, the black vertices. And a message could be any string of 0 and 1 on these vertices. So say 1, 1, 0, 0, 0 is one message. But not every message is a legal coded message. Some of them are message with errors. So how do I detect the error? So this is why I'm using the right part of the graph, where the vertices there represent checks. Each of them check if the message is correct. And what it checks is just it sums up the ones on the vertices that it touches. So for instance, if I were to send the message, if you were Bob and you received the message 11000, and then you look at the checks, you see that this is not a correct message. In the first vertex C1, there is a mistake, and the last vertex, there is also a mistake. And that way you can detect the mistakes, and sometimes you can even use this graph representation to decode even the wrong message into the correct one. Okay, so this is how codes are being represented by graphs. The question is, which graphs give you good error correcting codes? And an observation that won't get into the technicalities of what does it mean to be random, but the point is that if the graph behaves very random, like you can't really, there are no bottlenecks, for instance, in the graph. Every two sets of vertices in the graph kind of have a lot of edges going between them. So such a random behavior in graphs gives you good codes. Okay, so we're looking for random graphs in order to construct good codes, but there is a slight problem in this way of thinking is because how can you construct random objects? I mean, it actually looks counterintuitive. If you constructed it, it's no longer random. And we definitely need to construct it in order to build codes on our computers, on each of our phones. And we need to produce codes in to all of our digital devices. So fortunately, this is not the case. It's not true that we cannot construct almost random things. We are in fact able to construct, we are in fact able to give explicit construction, explicit objects, explicit graphs that behaves very close to random, or what we call pseudo-random. So one excellent source of such explicit but pseudo-random objects is number theory. And I've given you one example here. This is an example of how points are placed on a sphere, or just a small segment from the sphere. And without getting into the technicalities, on the left, you see a placement of random points on the sphere. On the right part, on the rightmost image, you see the opposite of random. It's a very rigid, very structured. And in the middle, you see an object coming from number theory, placement of points according to some number theoretic laws, very simple number theoretic laws, which I don't have time to explain. And looking at it kind of suggests that random number theory, the picture of the random number theory, it looks very close to the random picture. Okay, let me show you a more concrete example, which is related to the topic of this talk. Let me show you how you can construct a pseudo-random graph using a prime P. So for concreteness, let's take the prime to be 617. And here is the graph that you construct. So the vertices of the graph are just the integers 0, 1, 2, up until P minus 1, and you place them on the boundary of a circle. And each such vertex, each such integer, you connect it to 3 other vertices. So to x plus 1, x minus 1, that way you get the circle, and to the number 1 over x in modulo P arithmetic. So for example, 3 is connected to 4 and 2, and it's connected to 206, because in modulo arithmetic, if you take 206 and multiply it with 3, you get 1. And these graphs behave pseudo-random. Okay, so how can I claim such a thing? I mean, they're not random, they're explicit. How can I convince you that this graph behaves very close to a random graph? Well, I can claim it because I can prove it mathematically. And what stands behind this, the proof of such a claim are results coming from number theory. So here are the picture of two very famous number theorists, Tela Selberg and Srinivasa Ramanujan, and using their works and the results and theorems they prove in number theory, one can rigorously prove that the graph I showed you in the previous slide does display a lot of useful pseudo-random behavior. Okay, so in summary, what do? I take results from number theory, such as the Ramanujan conjecture. So here in the picture below, you see a stamp and you see an equation. This is the Ramanujan conjecture, and the stamp is a Belgian stamp with the picture of Pierre Deligne, a Belgian mathematician who proved the Ramanujan conjecture. So using such results, I'm able to construct explicit pseudo-random graphs. For example, Ramanujan graphs, and here is an example of a Ramanujan graph, which gives better and better error correcting codes in application. And that's it. Thank you very much for your time.
If anyone has any questions, please feel free.
Sorry. Natalie, please.
It might be a very silly question, but what you're trying to build basically is a better way of dealing with errors when we are sending messages, right?
Right.
Is it something that happens often? Because it feels to me as if the system is already pretty amazing at decoding messages.
Okay, so if I understand you correctly, you're asking, does errors even occur in our day-to-day life? So why do we need to correct errors if there are no errors? So I can't really I can't tell you that exactly which error occurs, because I think this is more of on the engineer part of the story, and I'm more dealing with the theoretical problem presented to me by computer scientists. But I would take my friends at their word when they say that errors are robust, and they are. I mean, there is no perfect system, and we as far as I know, we don't have a perfect channel of information that doesn't suffer from errors in it. So, trusting my friends, I would say that the system looks perfect because of the theory of error correcting codes, not because the channels are made of perfect material or something like that. Chetan?
Hey, can you hear me?
Yes. Hi.
So my question is, so you use a notion of pseudo-randomness, right? Is it computational pseudo-randomness, or is it another notion of pseudo-randomness that you use?
So can I ask, what do you mean by computational pseudo-randomness?
Something is computational pseudo-random if a bounded observer, a bounded Turing machine, cannot distinguish from truly random, and so this is what we use in cryptography, for example.
Okay, so it's not exactly pseudo-random. I mean, it does sound like a very interesting question, comparing the pseudo-randomness I'm thinking about with the pseudo-randomness you're describing. Let me very briefly, without making it into a full mathematical talk, the way I measure a graph being pseudo-random is I'm assuming that I'm just picking two large sets of vertices, and I'm just asking how many edges go in between them. So for a random graph, for me, a random graph is basically every edge is part of the graph with some fixed probability. And so I have an expectation of how many edges between those two sets of vertices should be. And if the number in my actual graph is close to that number of a random graph, I would, and if it's true for any two pairs of set of vertices, then I would say it's a pseudo-random graph. But it's very interesting to kind of compare it with your notion of Turing testing pseudo-random. I need to think about it more.
I see, thanks. So this sounds like a more statistical notion of pseudo-randomness. Thanks.
Balthazar?
Thanks, that was great. I just have a very simple question about the whole principle of coding. So when we encode a message, then does the size increase? And I mean, is this a worry, or is this an issue that there's a trade-off between, let's say, redundancy and size? Because I would think that like you want to transmit a lot of data, so that might be a concern.
Yeah, oh yeah, it's definitely, so you're absolutely right. Let me just repeat the question. A code has, among many other parameters, two important parameters to keep in mind is how much you're lengthening the original message. We have a name for it. It's called the rate of the code. If you lengthen it by a large amount, then the rate is very small and we don't consider it a very good code. Another parameter is how many errors I'm able to correct. That's also, it's the distance of the code. And as you rightfully suggested, we might want to find some balance between, I mean, you can correct a lot of errors if you lengthen the code, but that way the rate goes down to 0, or you can fix the rate and then you're not able to correct any single error. So you kind of want to find a sweet spot, and we have a mathematical notion of a good code. It's some sort of a construction which does have pretty good rate and simultaneously good distance. And we need to balance it, but they're not completely contradicting one another. You can have good rate and good distance simultaneously, and it's not trivial why, but we have, and we're using it.
Okay, thanks.
I don't really have a question. I wanted to make a little comment. I found it fascinating, remarkable, and to the pictures between the rigid and the random, and then the middle is very interesting, because in a way, you know, living life is like this. Like I work on meditation practices, right? And I think this mixture between spontaneity and structure, between randomness and order, is all over, right? So we have meditation practices that are visual, for example, where we impose reality. We say, we want to see it like this, and this is what we're going to see. And then we have the other extreme where they say, well, we just want it, whatever happens, happens. We're completely free, completely random in a way, right? And so there is some techniques that claim, like some religious traditions that claim that they have that they find ways to be explicitly spontaneous, to plan spontaneity, to plan randomness, right? So anyway, I think there is some connection there. Obviously, I would have to read up here on Ramanujan and the numbers theory, but I thought that it was a terrific talk, I was wondering whether there is any kind of connection to the way that you see reality in general, like when talking about these elements, or never, like as a scientist, how do you work?
So first of all, thank you for the comment. It's very interesting. I will need to think more about that. On a philosophical level, I can just say, I just have one thing that popped in mind when you describe this randomness in life. I once asked a friend of mine who works on the random issue and probability, and I asked him, what is randomness means? And he gave me a very short philosophical question. Randomness is everything you don't understand. So when you flip a coin, when you say it's a 50-50, that's because you just don't understand the friction with the air and the angular movements of the coin. So yeah, I'm not sure. I don't have a good answer to your question.
No.
But I'll think about it.
Great.
Yeah, thank you.
All right. Thanks again, Shai. That was great.